Good morning, ladies.
Good morning.
Well, I'm just waiting to see if anybody else joined us. Doesn't look like it. There we go. All right. Looks like we just get started then. All right, for this part, oh, I haven't moved this up yet. Hold on. I haven't moved the lecture up. Where's my mouse? So much stuff on here, it's hard to figure out where to put it. Mhm. I should move it. Not quite. Not quite. Still got a little bit longer. Mhm. Mhm. Trying to move it back where it belongs, but it's still hard because lecture. Mm. Here we go. There. Think I put it in the right place now. Yeah, there it goes. All right. Well, that was the last time. Oops. Hold on a minute. Stop this little guy for a minute. I guess he won't hear me. Hold on. I have to set it. No. Okay, there we go. All right. So let's see. Yeah, our next thing to do. Yeah, we completed that. So this is the rest of the lecture on limiting excess reagent, percent yield, and all the problems that are in slides 9 and 10. I did those. And so we are starting to review for the final. In order to do that, you need to go here and grab that. Now you can turn it in because I'm not going to do every single one of them. So you can turn it in for extra points if you complete it. Yeah, there we go. We're going to start with these first, converting to scientific notation. Just to remember, so I'm going to start with A. So in order to do that, you would have to remember, you have to count to where the decimal point is in front of a number between 1 and 9. So that would be here, right? So we moved it once. So that becomes 7.3 times 10 to the 1, since we moved it once. And it's also greater than 1. The next one I'm going to do is C. You do the same thing, but you have to also watch your sig figs. And the sig figs on this one, it's only 6.59. So you move your cursor 1, 2, 3, right? So 6.59 times 10 to the third. I'm going to do E. Same difference, so you write your number. And count 1, 2, 3, 4, 5. Oh, I skipped one. 1, 2, 3, 4, 5. I knew it. It's like, wait a minute, there's 5 on here. It's 4.58212. And yes, you do use all of them because they are all significant. Okay, for the next part, I'm going to do G. And this one is the opposite. Remember, you have to bring it to where it is exactly either 1 or 1 through 9. And on the first one, so you got to bring it 1, 2, 3. And this time it was less than 1, so it's a negative. Okay. And the last one I'm doing is I. And that is 21563. Okay. So we count them 1, 2, 3, 4, 5, 6. But only those are significant. So remember that 2.156 times 10 to the 6. Okay. You have to remember, just do the significant figures. All right. When you convert out of scientific notation, you have to do the opposite. You have to look at what you have. You have a negative. Okay. So my tip to you is whatever the number is, you put in one less zero than that. 1, 2, 3, 4, 5, 6, right? And then 6, 3. And that is your answer for that one. For C, it's going to be, so again, 3 zeros, 1, 2, 3, and then the number 5, 6. And for E, this time it doesn't work like that, so you do actually have to move it. So 7.56, so you're going to have to move it over 2, so it's 756.8. See? All right, let's clear those. And go to the next one. Okay, we have G. I'm just gonna put it up here. We're doing 2, right? So it's G. This one's times 10 to the 9, so you gotta move it 9 spots. 0, 0, 1, that's 3, right? 4, 5, 6, 7, 8, 9. Next one's I. And for that one, you have to move it -1, so it's the opposite direction, 0.085. That's it. Okay. No, sorry. No. Clear. Let me erase that because that's not right. One too many zeros. Sorry about that. Yeah, that's what that is. Somebody's going to come in. Where are they? Nope, it's not here. Okay. There we go. There we go. All right, so that's how you would do those. Now let's go to number 3. Yeah, we're gonna do the same thing. We're gonna do just the ones that, yeah, A, B, C. So we're gonna do A. A is, they want us to go 8.79 times 10 to the negative 4 liters to centimeter cube. Okay, so a liter, number goes down here. And if you're looking at the ladder, like I remember showing you, you're going from liter to milliliters. So that is 3 spots going down. So it's positive. Milliliter is the same as a centimeter, by the way. So this is going to give you 8.79 times 10 to the, also you're doing -4 plus 3, so it's -1 milliliters, which is equal to centimeter cube. Okay. Did you see how we did that? Okay. When you multiply, remember you add the exponents. That's where the -1 came from. All right. Let's clear that one and do C. This one says 117 milligrams to grams. 1 milligram down here. And you're going up. So it's 1 times 10 to the -3. Wait, oops. That does not look very nice. Let's do it again. -3. And that's grams, right? Which is what they want us to go. So when you multiply, you would get 117 times 10 to the -3 grams. But this is incorrect scientific notation, right? So we need to move it back 1, 2. If we move back 2, we add 2. So it's going to be 1.17 times 10 to the -1 grams. You see that? right? Let's see. E is going to be 101 centimeter cube. Okay. Oh, 0.3. 101.3. 0.3 centimeters cube to meters cube. Okay, so here's where the difference is. 1 centimeter is equal to 1 times 10 to the negative 3 meters. But they want it cubed, so we have to cube it, right? So once we're cubed, we're going to get 101.3 cubic centimeters over 1 cubic centimeter. Remember, 3 times 3 is 9. So 1 times 10 to the negative 9 meters cubed. Okay, now you can answer it. The answer would be 101.3 times 10 to the negative 9 cubic meters. However, we need to still move this back 1, 2. Since we're moving it 2 back, we add 2, right? So this becomes 1.013 times 10 to the negative 7. There you go. All right, and clear that one. We're doing G next, which is 2.5 liters to milliliters. Okay. This one's pretty easy, 2.5 liters. Say 1 liter contains 1 times 10 to the third milliliters, right? So the answer is 2.5 times 10 to the third milliliters. Okay. And the last one that we're doing is I, which is 536, no, 5.36, sorry, milliliters to liters, right? One times 10 to the negative 3, right? Because it's liters. So it's the answer is 5.36 times 10 to the negative 3. So 10 and liters. There you go. And that's how you do all of those. Like I said, you do the ones that I didn't do, which I don't know if you've noticed, but I've been doing I've been skipping one, basically, is what I've been doing. So let me highlight. Mouse, come on, mouse. There we go. Let me highlight the ones that I've done here. Okay, so I've done A. This mouse is not coming on for some reason. I have lost my mouse. Nope, it's not letting me do it. Okay, never mind. All right, let's do mouse. Okay, for this one, how many sig figs are there? Okay, so once again for A, remember what we do. We write down the number. When we look at the number, I'm writing it down, but you don't have to. And we are coming in from this direction because it has no decimal, right? So it is a an absence, so Atlantic side, remember? And we have 1, 2, 3. So the answer for this one is 3 sig figs. For C, we have a conversion factor, which is interesting because these are not sig figs. So the answer is an infinite number because that itself doesn't do sig figs. It's whatever you put in front of it, like whatever you're converting, that does the sig figs. B, we have 6,000 like this. We are starting on this end because it does have a decimal. So it's P for Pacific, remember? So we're going from Pacific to United States. So left to right, and we count all of them. So this one's 4. Then we have G. Once again, we have no decimal, right? So we're coming in from this angle, and we only have 2. Because the zeros in here don't count because you're starting from the right. Then the last one, I. We have 400 square meters. So in this case, it's only 1. Okay, and there you go. That's how you do sig figs. Remember, it depends whether you have a decimal or not. If you have a decimal, you start from left to right or Pacific, right? Atlantic, Pacific to United States. If you don't have a decimal, you start the opposite. You start from Atlantic, the Atlantic Ocean, right, to the United States, or right to left. All right, clear. And then the only ones that count are the non-zeros that are before the first, well, not only, but the first non-zero digit, and then everything else counts. So in this case, since we're coming from this direction, right, that was your first one. So then all the other ones counted too, so that's what made it 4. Here, this was your first non-zero, right? So only those 2 counted. See? Same here, this direction, so only that one counts. All right, clear. Boom. Now, we are doing conversions of temperature. For this one, we are going to need formulas. Okay. So we are doing A, right? Just so you know, we're doing A, C, E, and that's it. Okay. So A, C, and E. And I'm bringing them back down because I can have a little more room up here to write. Okay, so A. It's 115 Fahrenheit, right? To Celsius. Ooh, that's another year. Doesn't even look like it now. I did better there, but okay. All right, for that one, we need the formula with the C in it, right? Which is the Celsius. And for that one, we have that it is Fahrenheit minus 32. Do that first. That's what I'm putting in parentheses. And then you divide it by 1.8. So in this case, it's going to be 115 minus 32 divided by 1.8. That's going to give us, in my calculator, 115 minus 32 divided by 1.8. 46.1 degrees Celsius. Okay, there you go. That's 8. Let's clear that one and do C, which is 19 Celsius to Fahrenheit. In this case, we're using the F formula, which is 1.8 times your Celsius, which is 19, right? And then you add 32. So this is going to give me 1.8 times 19. That's 34.2 plus 32 is equal to 66.2 degrees Fahrenheit. Okay, and that's that one. Then we have E, where we're converting, no, just clear. We're converting Kelvin oh, 598. I forgot to write that part down, didn't I? 598 Kelvin to Celsius. Okay, so for that you need your Kelvin formula, your Celsius formula. So Celsius is going to be equal to your Kelvin minus 373. So in this case, it's going to be 598, right? Minus 273. And that is 325 degrees Celsius. Now, I'm going to go ahead and do F2 because that's a different one. And it also goes through all of the other that you need. So you have Fahrenheit to Kelvin. So in order to do that, the only connection that you have is going to be Celsius, and then you're going to change it to Kelvin. So first, we're going to do the C formula, right? Which is, remember, we had F, so the Fahrenheit, so 23 minus the 32 divided by the 1.8. That is negative 5 degrees. Celsius. All right, now we can do the Kelvin formula, which you take the Celsius and you add 273. So in this case, it's going to be negative 5 plus 273. It's going to be 268 Kelvin. Okay, there you are. clear all of that. And go to the next part where we have density problems. Okay, I am not going to do every single one of these again. Actually, they're all different, but you should be able to set these up on your own. So we'll do the first one. You know, it says the density of gold, and I'm just gonna call it DAU because a U is gold, right? And so we're gonna say the density of gold is 19.3, and that's grams per centimeter cube. Density of water, so we'll just dW is equal to 1.00 grams per centimeter cube. Now it says what mass of gold, no, what volume of water, sorry, volume of water, so we want dW, that's our question, would be equal to a mass of gold, so mass of gold that has 5 by 4 by 15. So all you have to do is multiply those, and 5 times 4 times 16 is equal to 15, sorry, clear. 5 times 4 times 16, I keep saying 16, 15. It's equal to 300 cubic centimeters. Okay, so you see what they're asking you to do first is to figure out the one thing you don't have of gold. So remember, density is equal to mass, and we can do this one with our, let me redo this. Remember our little triangle? I'm just going to use the triangle. Our density is equal to mass over volume. We want volume, so it's mass over density. So the mass is 300 cubic centimeters. We don't know the mass, sorry. That's the volume. So we're looking for the mass, which is 300 cubic centimeters times our 19.3 grams per cubic centimeter. See how that's going to end up canceling out the cubic centimeters. All right, so it's 300 times 19.3. That gives us this mass right here. So the mass of gold is going to be equal to 5,790 grams. All right. So far, so good, right? You getting that part? Okay. Because in order to find the mass, we needed the volume, and the volume is right here, right? By just multiplying that, you get the cubic centimeters, which is your volume. Now you apply your formula, which was this density times volume. We did that right here, right? Once we did that, we found out the mass of water. Now they're saying what volume of water would be equal to that. Well, since the mass of water would be equal to the volume of water, so we can say right? The mass of water would be equal to 5,790 then grams. And then we have that the mass of water is the same actually, so it's 1 gram that goes on the bottom for 1 cubic centimeter, see? So then the answer is 5,790 cubic centimeters, see? Does that make sense? Okay. That would be your answer. Your volume of water is that. Same as the mass of gold. Okay, let's clear that. Now, we did this one, right? So we're doing this one next. How many seconds are there in a leap year? Can anybody tell me how many days there are in a leap year? Anybody know? Hey Google, how many days in a leap year? Hey Google, how many days in a leap year? Okay, there you go. 366 days. I just call it D. All right. So for every 366 days, and they want us to calculate seconds. So 1 day has 24 hours, right? 1 hour has 60 minutes. And 1 minute has 60 seconds. Okay, so we went from days to hours to minutes. You see that? Now we'll just multiply 366 times 24 times 60 times 60. And we have our answer, which is a huge answer. It's 31,622,400 seconds. Or if you wanted to give this in scientific notation, it'd be 3.16224 times 10 to the that's 3, 6, and one more 7, right? Seconds. Okay, and there you go. And all of them being exact numbers, you need as many sig figs as you have. Okay, which was only 7. No, 6. Sorry. Yeah, 6. All right. And there's your answer. All right, the next one we're doing is this one. Let me clear that. Okay. It says the density of a substance is 23.7. Remember, whenever they do grams per milliliter, that just means for every that many grams, you have 1 milliliter. That's it. All right, so they want us to change it to grams per liter. All right, so 1 gram is equal to 10 or 1 times 10 to the negative 3. Oh, that's milligrams, sorry. That's milliliters. All right, yeah. So this is the opposite, 10 to the positive 3. I don't know what I was thinking. Grams. Okay, right? So that's done. That has now changed to grams, right? Except this is backwards because the milligrams has to be on the bottom. You see that? That's why I said I don't know what I've done because that was backwards. Now we need to flip it. You know, when we flip it, and then it is 1 milligram is equal to 10 to the negative 3 grams, right? All right, now we need to change the milliliters. So we say 1 milliliter is equal to 1 times 10 to the negative 3. No, positive 3, sorry. Yeah, what is it? I'm backwards today. Positive 3 liters, right? No, it's not. It's negative 3 still. I was right. I'm not backwards. Okay. So once you do that, you can see that these two are going to cancel each other, right? So the answer is actually the same. And the reason it is because the ratios are the same, right? Okay. But we did get rid of milligrams, right? And milliliters. See, they're gone. And we changed it to grams, which is what we wanted, per liter. And there it is. All right. Now let's clear that. And we're going to the next one. We now need to, oh, and by the way, here it should say decimeter. Oh, sorry, here it should say, not there. Here it should say decimeter cube. Okay. When we have millimeters, okay, remember this is the same thing as we've been doing before. It's just going to be a little complicated. So we're going to do A and C. A is 1 millimeter cube is equal to how many meters, right? All right. Oh, I'm backwards again. I'm backwards today. I don't know why. Okay. Now, for every meter, we have 1 times 10 to the second, right? Third millimeters. Okay. Yeah, I was already thinking ahead. That's why I did second. But this is not when you cube it. So when you cube it, you're going to actually get 10 to the 6. And this is still going to be 1, and that's going to cancel with that. So the answer is 1 times 10 to the 6 millimeter cube. You see that? Okay, that's a 2. Okay, clear now. So you can put that here, 1 times 10 to the 6. The next one is millimeter again, but we're changing it to centimeter. So for every millimeter, we have 1 times 10 to the 1 centimeters. Actually -1, right? Because it's backwards. We're going up. In this case, we are. All right, so now we cube it. I mean, we square, no, not cube it, square it, because we don't have a way to cancel it if we don't. So the answer is going to be 2 times 1, so 1 times 10 to the negative 2 cubic centimeter. I mean, cubic, square centimeters. You see that? It's the same number. You just got to make sure that you square it. That's all. And the answer for that one is 1 times 10 to the negative 2. Okay. All right. That's that one. Let's clear those. Now we're going to our next set of problems. And we have 2 of them. So I'm just going to do 12. But I'm going to do it up here so that you can see the whole setup. Okay. So the question is, see, we have to always read what we have. A patient takes, and you can always write down these things too. See, if you write down what it's telling you, it says 125, it says micrograms per day. It also is telling you that it's 125 micrograms for 1 tablet, right? It also is telling you that you have 1 tablet for 1 day. It's telling you all those things. You see that? So they're asking you how many milligrams are there in 1 month supply or 30 days, right? So we're starting with this, right? Because we first have to figure out how many. Okay, so out of those, the one that makes sense is this one, right? Because we have 1 tablet per day, so we know that that's an equivalent thing. Okay, so we start for every day, we have 125 micrograms. But didn't they ask us how many milligrams there are? Okay, so 1 microgram. And if you go on your ladder, you will see that you're going to have to go up to milligrams, and you're going to go up 3, right? Okay, so it's 1 times 10 to the negative 3 milligrams, right? See that? All right, so all we have to do is multiply, divide, and we've got 30, clear, 30 times 125, and that gives me 3. Okay, let's say you don't have a calculator that does this kind of math, so it's give me 3,750 times 10 to the negative 3 milligrams, right? That's the answer. But remember, you got to go 1, 2, 3. So it's 3.75. And we went 3, right? So plus 3 gives me 0. So there's your answer. See? 3.75 milligrams. Or, in this case, you really didn't have a real sig fig. And so you're fine with this, because you don't want to give this person too much. So all of these are conversions per month, right? Okay, and there you go. So that's how you would do it. Just gotta make sure you realize what they're telling you. See how they're telling you. Takes 1 milligram tablet per day. You see that? So it was telling me all of this, that for every day, right? Every tablet, it would be that. Every tablet you have a day. So you could have done both of these, or you could have just done this one, which is what it's really telling you, which is what we used. Okay, let's clear that. Go to the next one. Okay, for the next one, I think it's easy enough for you to know. Okay. Which state of matter is represented by each of the following? Okay. You guys tell me. Ice would be what? Well, that would be a solid, right? A rock would also be a solid. Clouds would be a gas. Air would be a gas. Hydrogen in the sun, that would be plasma. And vegetable oil would be a liquid. And there you go. Now, chemical or physical change. Electrolysis of water, that means it's breaking it up. That is a chemical. Fog formation is a physical. Oops. Let me do better than that. Physical. Rusting of iron, chemical. Separating alcohol water, physical. Burning wood, chemical. Converting sand to glass, physical. Okay. Now, for this one, you don't have to draw it. Just go look at your face of matter drawings. Make sure that you know what you're doing, because we may ask you questions about them on your final. To make sure you know when you see the like this, like that. Remember, that's your melting point, that's your boiling point. Here you have solid in this area. Here you have liquid, and here you have gas, right? And this last little thing wasn't supposed to be here, but that's all right. Okay. Boiling point, melting point. And if you're coming backwards, then obviously it's condensation point and freezing point, right? If you go backwards. So, okay, the next ones are either mixture, solution, or compound. Okay, soda pop is a mixture. Baking soda is a compound. Sugar is a compound. Milk's a mixture. Pizza's a mixture. Muddy water is a mixture. Bronze is also, actually, in this case, oops, I just saw something. That one is actually a solution, right? And so is this one. Okay. So remember, solution is a mixture, but it's a homogeneous mixture, right? All right, let's go clear this and go to the next part. Now, the definitions there for you. You are going to define all of these yourselves. So they're already there. You got them. Now, for this one, what they're asking us to do is to And let's add plasma to it, and just because we can. Okay, so temperature ranking obviously be 1 through 4 now. Plasma would be 1, gas would be 2, then 3, then 4, right? 4 being the highest. Oh no, that's backwards, isn't it? All right, so we just erase that and go back again because that was wrong. We need to read our instructions. So it's 4, 3, 2, 1, right? And see, it says being the highest. Okay. So kinetic energy, 4, 3, 2, 1 also. Distance between molecules is going to be about the same here, but let's do that also. But the intermolecular forces are going to be the strongest in a solid, then a liquid, then a gas. Okay, see that? This is one of the things that you need to know. The one thing that's different is the intermolecular forces, because the closer you are, the more attracted you're going to be to each other, right? So that makes sense. And since the molecules are lower, right, they have less energy, the temperature is lower, then the molecular forces are the highest. And that's how they go. All right, now let's go to the next part on the mouse here. Okay. Periodic table, bonding. Okay, so this is where we're going to stop today. All right, it says which atom's radius is bigger, bismuth or phosphorus, rubidium or antimony, and why? Well, first of all, you need a periodic table. Without one, there's no way you can tell. All right. Remember, atomic radius increases from right, oops, I thought I had nothing. Increases from right to left and down, right? So remember that, okay? That's why. This is the answer why, okay? Now, phosphorus happens to be more like right here, right? And bismuth happens to be like right here. So the answer is bismuth, right? That would be correct. So we're just going to highlight, so circle it, I mean. All right. Now, as far as magnesium, and why? The answer why is because we have, this one is lower, right? On the periodic table, same group, but lower. And it is, and so therefore it has more layers, more, not layers, but more orbitals, more, you know, atom layers, I guess you could say, kind of like an onion, right? All right, the rest is rubidium. Rubidium is right here somewhere, right? And antimony is actually right here, right before there. So obviously this one's the larger one. Why? Because it's farthest to the right and also lower, for both of the reasons, right? Okay, so rubidium is the highest. Okay, now let's clear that. So we have the answers. I'm just gonna redo that. Bismuth, rubidium. Okay. Now, as far as bigger, which one is it? Well, magnesium has, normally, magnesium has 3. So this is your nucleus, right? Then you have 1 with 2 electrons. And you have the second one, which has 8 electrons. Right? And then the last one, which was only 2. Okay. Okay. So when magnesium becomes an ion, those 2 electrons are gone, right? Which means this whole layer is gone. So that before was magnesium. This is now magnesium 2 plus, right? So which one was larger? Magnesium, right? All right, let's clear that. All right, the next one is selenium. Well, normally selenium would have the same kind of thing. You would have your nucleus. You have 1, 2, 3 layers, and I'm not doing those anymore, but the last one would have 6 electrons, right? Which would be missing 2. Oops, did not mean to erase all of that, just the 1. So just an undo. Okay, so when it joins with something else, it gets 2 more. It's gonna make those, yeah, okay. So now the balance that you had in the nucleus, where the positives were equal to the negatives, is gone because you have just added 2 electrons. So selenium goes and it expands. Okay, selenide ion expands. So the answer here is this one. Okay, let's clear that. Well, yeah, it's clear on that. All right, so once again, I can just redo these. Okay. Then which one is more electronegative? Electronegativity increases going left to right and up towards fluorine. So if gallium is right here somewhere and selenium is right here somewhere, obviously selenium is going to be more electronegative, right? If chlorine is over here somewhere, put it right here, and astatine is over here somewhere, obviously it's going to be chlorine, right? Okay. And then the last thing that we have is electron affinity. Now, electron affinity can include the noble gases. Why can it include the noble gases? Because it is how strongly they hold on to their ions. And they're the ones that don't want to let go, right? Okay, so let's start with ytterbium. Sorry, yttrium. Let's call it ytterbium. Yttrium, let's say it's right here somewhere. And then we have technetium, which is right here somewhere. Okay, so obviously technetium wins, right? And then helium's way over here, and radon is way down here. So obviously helium wins. And there you go. That's the whole answer for that one. You have to remember your trends, okay? Trends are very simple. If you remember, oops, I was going to erase that I had gotten it. Okay, if you remember this, the only one that goes backwards, okay, just remember this, is this one, which is atomic radius. All the others, and I mean all the others, are going to increase this way, okay? That's going to be electronegativity, ionization energy, and lazy, but I might as well write it down, and electron affinity. Now, the only difference here is electron affinity includes the noble gases, okay? The other two do not, because there is no way that they'll make ions, so they're not going to give up their electrons. Therefore, nothing that gives up electrons is going to be part of it. But holding on to electrons, it will. Okay. So electron affinity is definitely including noble gases. All right, remember that. All right, clear that. Okay, next time we will do these. And we'll be done doing all our amazing, right? We'll be done doing a review. If we don't finish, that's fine. If you have any questions between then and now, make sure to ask them next time that I see you. Go ahead and finish the parts that, so this is where we stop, right? Part 2, number 1. Okay, remember that. We're still on part 2 over here, but we're not doing that one just yet, because we are past the time, so that's enough. We'll do it next time, okay? All right, ladies, you have a great rest of your Monday. And I will talk to you later. Bye.